Welcome to qnawire.
Three parts. One is when the person slides on the water side. Here, the mechanical energy is conserved, and then he gets attached, or there's a collision with him with the rod, vertical rod, and at this point, the angular momentum is conserved, and once he swings with the vertical pole at this part, mechanical energy is conserved again. So let me draw three separate borders. One is this one where mechanical energy is conserved. Then at this part, during collision, the angular momentum is conserved, and this part where mechanical energy is conserved as well. So on the side and after the collision, that means here and here, um, as we said, mechanical energy is conserved, so we'll be using k1u1 plus k1u1 equals to k2 plus u2, where this is the energy before or in at the initial stage, and this is the final stage. So in this part, the initial point is here at height h, and the final point is here just before the collision. And also we're given the moment of inertia of the pole, which is 1/3 ml squared, where big M is the mass of the pole and L is the length. Also, we need to figure out the angular momentum of the pole person system. Now, the initial angular momentum of the person is mvr, where m is the mass of the person, which is in our case mvl, because this is fixed around here. The pole is fixed around here, so that means, and the pole is swinging on its axle, and the length of the pole is L. So that's why we have mv as in the momentum of the person. So that means when the person is here, here's a momentum of mv, and then the radial vector L is multiplied to that to get the momentum. Now, one more thing we need is the angular momentum of the pole and person system. So for that case, we'll add the pole's moment of inertia with the person's moment of inertia, and then we multiply omega with it. So that's when we have pole and person system. So pole and person, and this is when this is the this is the angular momentum of the person. And this is that, and this is that. And if we evaluate this, we see that it's going to be 1/3 ml squared plus little ml squared times omega. And also kinetic energy after the collision there will be a rotational part involved in the kinetic energy. So we need that around here when we solve the mechanical energy conservation. So for that case, kinetic energy after collision will be half of I omega squared, where again I is the total moment of inertia because it's a pole person system. So that's going to be half of 1/3 ml squared plus ml squared, and then we multiply that with omega squared. So there's a multiplication with omega. So we have few equations that or few useful equations that we'll be using. So we should note this one, this equation, and of course we'll be using this one as well. So let's work backwards, or in other words, let's start with this and then we will work our way till we get the height. So first will be, as we mentioned, that we'll be using mechanical energy conservation. So let's actually write that. So this is mechanical energy conservation, this is angular momentum conservation, and this is mechanical energy conservation again. So we're starting with this one. So for mechanical energy conservation, we have K1 U1 equals K2 U2. And so this is when the person gets attached to the pole, or in other words, this part. So here we'll have the potential energy and the kinetic energy of the person and pole system. So kinetic energy is K1, and we have potential energy of the person, and we added that with the potential energy of the pole. Then there's so this is the final position. So this is position 2, this is number 2, and this is number 1. So actually here K1 U1 is denoted at this point. So we have kinetic energy, we have potential and of the person and potential energy of the pole. Then at point 2, so just let me draw it one more time around here. So this is point number 2, point number 1, and here we don't have any kinetic energy because it swings and stops around here, then it goes back, so that means there's no kinetic energy here, but we have potential energy. Now we see that at this point we have the rotational kinetic energy, and we have already calculated this part, so we'll use that here. Then for the person, there's no potential energy, because if we say this is our ground, then we set y equals to 0. And for the pole, we'll actually consider the center of mass of the pole instead of the whole mass. So its center of mass is actually centered around the pole, which is a height from the ground to L by 2. So that's why we have a non-zero potential energy for the pole, which is mg times mg times the height, where height is L by 2. And then at this part, we have the potential energy of the pole and we have the potential energy of the person. So this is the person's potential energy, and the way we calculate that is we calculate the height of this. So we see this is L and this is theta, so that means this part right here is L cosine theta, right? And we subtract this part from this whole length to get this distance, right? So let's mark that distance with red bracket. So this part is the change in potential energy for the person. So what we did here is we subtracted mg L from this part, L cosine theta, and then we took L outside, and then we have 1 minus cosine theta. Similarly, we did this part as well, but the only change here is the center of mass is centered around here, so we just did the same calculation with L by 2. So that means we have L by 2, and then we added that to L by 2 times 1 minus cosine theta. So that's the potential energy at this point. And from here, if we solve for omega, we get this expression, and we're already given the mass of the person and mass of the pole and theta, which is 72 degrees. So using all those numbers, we see that omega is 1.54 radians per second. Now we'll be using conservation of angular momentum, or in other words, we'll be using this part of the equation. So for the conservation of angular momentum, as we mentioned, before collision, the person had mvl, or the total angular momentum was mvl, and after collision, it's the total moment of inertia times omega, where we have already calculated these two here. So this is before collision and this part is after collision, so we set them equal to each other, and from there we actually solve for the velocity, or the linear velocity. So if we do so, we already know omega, L, M, big M, and small m, and from there we see that the linear velocity is 10.3 meters per second. Now, since we know the linear velocity, we move on to this part, or the final part, and here we'll be again using the conservation of energy. And here we have u, so again we'll be using k1 plus u1 equals k2 plus u2, where this 1 is here, so let me use green marks for that. So this is point number 1, and for this becomes point number 2. So at point number 1, we don't have any kinetic energy, all we have is the potential, so that's why we have mgh. Then at point number 2, or at the base, there's no potential energy because we considered that as our ground, so all we have is the kinetic energy. So from there, if we solve for h, we see it's v squared over 2g, and we already calculated v from the previous parts. So we put v there and g there and see that height is 5.41 meters. So to recap, we started from this part over here, and we solved for omega. We extracted the information omega from there, and we use this omega information to find out the linear velocity. Once we got the linear velocity from the middle part, we use that in the final part, or the left part, and we solve for the height. Thank you.